All right, everyone, we are back, and we are going to go through our block diagram algebra and transfer function derivations. Ugh, that's a tongue twister. So we have been working so far, and we're kind of familiar with some of these systems. Now, remember, we've been dealing with like undercase for the time function, but now we're looking at our transfer functions or Laplace transform values here. Again, that's what the capital letters indicate. So it's really, really important to kind of denote that. So these are the functions that are in the ESTO name. So we know our reference, we know our basically control, transfer function. We have our plant function, that's our equations of motion. Our output, air in the unity feedback system is just the reference minus essentially that output, that ideal signal. And then U of S is going to be our control effort, which is going to be equal to this, and we're going to derive this. And D of S is essentially our disturbance. It's basically an input added before the plant. And N of S is going to be in the noise. Now, I think it's good. It's a good idea to kind of walk through all the different types of block diagrams that you can see, and how they can be used, and just so that you can kind of denote them. So this is an open loop transfer function. There's no feedback here. This is the toaster. So the reference goes into the controller, control command, plant function, and then your output. And that's it. So if I wanted to define my U, basically this U of S, it is going to be equal to the input, right? So if I were to do, and we'll do this once, U of S is equal to the output, which is going to be, and we can kind of see that here, it is just going to be our output, which is going to be R of S. Oops, let me see here. Apologies for that. Basically, something was going on in the recording. The computer died. So if we want to do essentially the block diagram algebra, I like to focus first on deriving basically the transfer functions for basically the plant and the controller, anything that's boxed. I like to define those first, and then we can use it to write the full transfer function for the entire system. So basically, again, that input over the output that we're looking for. So if I look at C, my C of S, the output is going to be my U of S. The input is going to be my R of S. For my plant, P of S is equal to output, which is Y of S, over U of S. Now we can leverage and rearrange these expressions to basically get a relationship for each of these other values here. So you can kind of see, you could rearrange C of S here to get us a value of what is that U of S in terms of C and R, Y of S rearrange in terms of just the plant, and then you can substitute in this for this, and then you can get a function for Y in terms of R, in terms of all these values, and you get this C of S times P of S. That's it. It's literally block diagram algebra, but again, these transfer functions that describe, again, the input of the control function and the output is extremely important and extremely valuable. So we really need to make sure that we can kind of do that for all different types of systems. And this is, again, the open loop response from input to output without feedback. It's typically will be defined as L of S, open loop transfer function, although, again, it varies. So it's good to know kind of this. It's good to know that how to derive these out by hand. This is our closed loop unity feedback. So kind of same idea here, right? So my C of S is equal to output, which is my U of S, over E of S. And we know our E of S as well, when we see this kind of little node here, my E of S is going to be equal to, let's follow the line, is equal to Y of S minus, so here, Y minus R gives me E. So Y minus R of S. So we have this function here. We have this function here. We also have in the plant, again, Y of S over U of S. And we can manipulate, and we can just do algebra to write out these functions. And what you'll end up with, if we write Y of S in terms of R of S, you'll get this final transfer function as well. So this is the closed loop transfer function from reference to output for our unity feedback closed loop system. Great. So we've done these before, this is the closed loop. We've talked about it. What about if there's a disturbance? So let's add some disturbance here, W of S. That's a little bit different. Where's it? Disturbance can be D of S, or it could be W of S. I probably need to redefine that. But anyways, if we have some disturbance here, and let's say we add it right before essentially it gets to the plant. So there's some control, and let's say there's some, disturbance to the system, some air, something that's, I always think of our inverted pendulum, and there's some disturbance, there's some vibration, something's going on, right? So again, but it's the same formalism, right? So how do we write out C? So C of S is equal to U of S over E of S. E of S is still going to be equal to Y of S minus R of S. So the only thing here now that's basically changing here is what's going into our plant, our P of S. So we can actually go ahead, where are we at here? We can actually write out and kind of see how that is going to respond. So if I'm looking at my P of S right here, so my P of S is equal to basically my U of S, I think it's going to be plus my W of S, because we're just basically adding that in there, over my output, which is my Y of S. And you can see that's essentially how we're rewriting that function here. So, excuse me, it should be, that's not good. Always output over input. I'll make sure I'm not doing that incorrectly. No, I did that correctly here. So Y of S over that U of S plus. It doesn't implicitly say plus, but I mean, we can kind of add that in there. WS here, and then that's where you rearrange. So we've got this function, we got this function, we got this function. We've defined everything again, and again, you could rearrange the system, and now your Y of S is going to be basically represented like so. So how your reference and disturbance are going to change essentially some of these values here, and how you can get eventually you can get that transfer function. We're going to have a nice dandy table too to kind of show us that. What if there's, again, some noise? So let's go ahead. C of S equals U of S over E of S. We know what E of S is. Tell me if you're getting bored, but it's always good to do this. So now it's going to be E of S, though, in this scenario, so we have is equal to Y of S plus V of S minus R of S. And the plant is just going to be equal to, plant of S is equal to Y of S over U of S. There you go. You can kind of see E of S is that R minus this plus this. So, or actually it just depends on, actually did a little bit. R of S, is equal to, because we're starting from over there. That air is this minus, basically V of S plus, which is also another minus, Y of S. Kind of the same idea. And you'll substitute it in, and then you can get essentially that response on your system. And there you go. And you can rearrange essentially the function. And finally, the most general case right here, and then we can find a real nasty essentially function here, but essentially that's how we're going to do it. So key takeaways, you can kind of see this for the open loop transfer function. You see kind of this term dominating and basically appearing in the denominator. So here, here, and here. It's really, really, really important. Feedback will attenuate disturbances, and then again, we're governed by this equation. But these are going to come into play a little bit later in future lectures. So that's it. Your first control lecture. Very important foundation, and we'll see you in the next video. Thanks. Bye.